represent Newton's second law with a non-zero F-net due to gravity and drag. I videoed my friend dropping a beach ball and clipped the frames so that the bounce was not shown. This is the clip of the motion. So basically the origin of the axes was placed on the center of the ball on the first frame, and the motion continues in the negative y direction. The initial velocity used is 0 meters per second because the first frame is the ball right before it was released. This over here is my graph of the motion. As you can see, it's clearly not linear. This indicates that there is not constant velocity and that the net force, or total pushes and pulls on the beach ball, is also non-zero. The ball is acted on by the earth and the air while falling, so that makes sense. So basically with that, both the gravity and the drag force have to be included. And so this is basically done by adding up the vectors for gravity and drag force to get the F-net. And so this is shown here. This is basically just to give the outline. Gravity is the negative y unit vector times mass times the gravity constant. And drag is the negative b constant times the magnitude of velocity squared times the direction of the velocity, times the unit vector of the velocity. So basically, this is the code that was set up for F-net. Here you have the line for the weight force or the gravity, which is the ball mass times the gravity times the negative j hat. And then you also have the drag force, which is the negative ball, or negative b, times the magnitude of the ball velocity times ball velocity. And then the F-net here is clearly the weight force plus the drag force. So this goes back into Newton's second law, where the final velocity equals the initial velocity plus the F-net divided by the mass times the time. So the weight force and the drag will fall under the F-net here. And because this is going to be positive, so the velocity will increase, which makes sense according to the clip, as the ball fell faster throughout the frames. When the model runs, the motion appears generally correct, as the ball does fall in the negative x direction, or the negative y direction. So as you can see here, it's falling. From here, the model data was compared with the experimental data to see if it's a good representation of the forces involved. I graphed the time in seconds versus the position on the y-axis in meters for the experimental data, which is the blue line, the model with drag and gravity, which is the red line, and the model with just gravity, which is the orange line. So basically, you can see here that the red line is a much better fit for the particular beach ball in this case. That makes a lot of sense because the beach ball is a large object, but it has very small mass, so it would be very susceptible to air resistance and drag force. So what if the ball was thrown down instead of just dropped? This means the initial velocity would no longer be 0, and the curve would be more straight. So the ball would fall much faster than the original model. As you can can see this is a much steeper decrease than the original graph that we had, which obviously would be a different kind of model. So it's important that we took into consideration the initial resting point. So what does all this mean? For this model, drag is necessary because of the shape and the mass of the beach ball. But if it were something more dense, drag would have a smaller influence, and the gravity would have basically the only effect. So in that case, if we had dropped like a baseball, it's more likely that it would fit the gravity curve only.